Schneid guy.
So we're going to talk about the resting membrane potential, abbreviated here RMP. We also can refer to it as the V rest, which V for voltage, rest indicating that the cell is in the resting state. We can look over here in the cell. We can see that there's the cell membrane, the outside of the cell, and then there's the inside. And we notice that there's a concentration gradient of sodium high on the outside relative to the inside. Potassium high on the inside relative to the outside. And we see here our sodium potassium ATPase pump that uses ATP hydrolysis to have the 3 sodiums out and the 2 potassiums in to maintain this concentration gradient. So right now, there's no conductance, there's no channels for any of these ions. And so we can say that the VM is just equal to 0 in this example where there's no conductance, there's no channels. And what we're going to do is we're going to add some channels first for potassium just to kind of start and build what this is going to look like. And so we can put those channels in, and we call this now leak potassium channels. That's what they're called, these ones that are just there at rest. And then we can show potassium now leaving down its concentration gradient, leaving the cell through these channels. And remember, as potassium leaves, it's going to leave negative charges behind, and that is going to cause the membrane potential to become more negative. So we can see here that we have introduction of these potassium channels. So that creates a large G potassium. We have potassium leaving the cell, and then the membrane potential becomes negative. And once it equals the equilibrium potential for potassium, because that's what it will continue to do, it'll continue to leave, making the cell more and more negative until it reaches the equilibrium potential for potassium. And once it's equal to the equilibrium potential for potassium, then the I potassium is going to be equal to 0. And so if we wanted to see what this would look like in a different way, we see here we have on the axis, this is just going to be time down here in milliseconds going along. On the y-axis, we just have the membrane potential in millivolts. There's just 0 for reference. And we said we were starting at 0, and that's where our membrane potential was before we introduced the channels. And now we have the membrane potential at rest is going to be, let's say, down here someplace, is moving along. See how it's stable and it's resting? And that would be exactly the E potassium, okay? So the membrane potential would be equal to the E potassium. This would be with no sodium conductance, all entirely 100%. Now, what if we added some sodium channels into the picture? We can do that. So now I'm going to add sodium leak, and the sodium is going to go into the cell down its concentration gradient. And as sodium goes into the cell, the membrane potential is now going to become a little less negative than it was. We can take a look at what that would be. And remember, the sodium equilibrium potential is positive under normal conditions. And our membrane potential at rest before was right at the equilibrium potential for potassium. So now as the sodium, now we're going to have a situation where the membrane potential at rest is, instead of going to be right at E potassium, it's actually going to start to go up towards the equilibrium potential for sodium. Sodium goes in, the new membrane potential is going to be increased at some number that is less negative than the equilibrium potential for potassium. It's going to be getting closer to the equilibrium potential for sodium. It's not going to be that close to sodium because the conductance for sodium is less at rest than for potassium. Remember, we drew in a lot of leaky potassium channel, a lot of conductance at rest for potassium, and not as much for sodium. So if we were going to write in terms of Ohm's law equations, our sodium and potassium currents are going to And remember that the potassium current is a positive current. That's an outward cationic current. And the sodium current is an inward current. That's negative for cations. And those are going to be balance each other at rest. And those have to be zero now, where these are. Expand this out using Ohm's law, we can see that the conductance of potassium times the difference between the membrane potential, in this case at rest, and the equilibrium potential for potassium. That's the driving force. We can do the same for sodium, multiplied by its driving force. Right now we've expanded out the current equation, and we can see that because the high conductance of all those channels we drew in for, right, this is a high value, and the difference between the membrane potential at rest and equilibrium potential for potassium, that's a small difference. So this is going to be a small number. They're going to be close together. And the profile is really reversed, right? This is a high number. The conductance is a low number. The difference between the equilibrium potential of sodium and the resting membrane potential is a large number. Now, the reason why these add up to zero is that the number for sodium, this is a negative number, right? And for potassium, it's a positive number. Remember, we talked about positive and negative currents. So what we end up with is these being equal to each other in terms of their absolute value. Okay, so we end up with a number that is the same value, but of opposite sign. And so when we add them together, we have no net current, no net movement of ions when we consider sodium and potassium